Okay, so we have two goals for today. One is to go over the cited derivative exercises. It's understood that this is all kind of new for you, and so we want to make sure that there are no confusions about things. Second, we are going to leverage these cited derivatives in order to talk about what happens when f prime does not exist. So, in short, we're going to take a look at homework, and then we're going to look at what we call non-differentiability. In other words, under what circumstances does f prime of c fail to exist? So that's our goal. And I'm going to go back and forth between the Smart Notebook and the homework here, just so we can see what's going on. In number one, we're supposed to compute the derivative from the right and the derivative from the left at c. And when I look at function a, it strikes me that function a is a polynomial. And I know the derivative of a polynomial, so that f prime of x is equal to 2c, which means that f prime of 3 is equal to 6, which means automatically that both the derivative from the left and the derivative from the right at 3 must both be 6. So that's easy enough. But now we get to f of x equals the absolute value of x, and things look a little bit different. I remember that for f of x equals the absolute value of x, that the derivative is equal to x over the absolute value of x, and there is one value of x that this does not make any sense at, x equals 0, which just happens to be the value that we're looking at. So because I cannot use the formula for the derivative, because the derivative does not exist at this point, instead I must use the limit definition. And I'm going to set it up so that I have the derivative from the left on the left and the derivative from the right on the right. And we're going to use our limit definition and write the derivative as the limit as x goes to 0 from the left of f of x minus f of 0 over x minus 0. But this is a familiar limit to us. We've seen this limit before. What's its value? It's negative 1. That's exactly right. Take any negative number close to 0, take its absolute value, divide to the negative 1. Meanwhile, over here, same song, second verse, we have the exact same difference quotient, but now we're approaching 0 from the right, and we get a positive 1. And now we understand why the derivative fails to exist at 0, because the derivative from the left and the right have different values. Now here's what this means for our function. If I look at the graph of f of x equals the absolute value of x, and I start at x equals 0 and go to the left in the direction of the curve, the slope that I get will be negative 1. But if I do the very same thing, I should have done that in blue. I'll tell you what, I will actually undo that so we can do it in blue. Here we go. But the very same process, starting at f of 0 and going now this way along the curve, gives me a completely different slope, which is positive 1. That's the mean of that. Okay. And so we're happy. Yeah. Well, let's take a look now at the third question in A. Here, f of x equals x squared minus 3, x is less than or equal to 2, etc. And I'll copy this one to the notebook as well. Okay, and so here is our f of x. And now they ask us to find the derivative derivative from the left at 2 and the derivative from the right at 2. Now I want to observe that this question is interesting because f of x is a piecewise defined function. And if I were to take the derivative of f, then for each of the interiors of the domains, I'm looking at simply a polynomial in the first case, a quadratic polynomial, and I'm looking at a linear function in the second case. And this applies for x's that are less than 2 and for x's that are greater than 2. But right when x equals 2, on one side of 2, my function is one type of function. On the other side of 2, my function is a different type of function, and the rate of change may not be consistent or equal from those directions. And so, right at the joint where the two pieces come together, it will be necessary to use the limit definition. I will not be able to use my derivative rules. Let me draw this so you can see what I'm talking about. Here is f of x. For x's that are less than 2, I have a nice quadratic polynomial. For x's that are greater than 2, I'm going to have a linear function that looks like this. And it may very well be the case that when my linear function comes down to the point 2, 1, where the two pieces join together, that it may have a different rate of change than my quadratic polynomial. That's why I cannot use derivative rules here. Because in any neighborhood of x equals 2, my function is neither quadratic nor linear, but it's this piecewise. Does that make sense? So I can use derivative rules in the interior for any x less than 2, and for any x greater than 2, but I can't use it at x equals 2. At x equals 2, we do the limit definition. We're going to say that this is equal to the limit as x goes to 2 from the left of f of x minus f of 2. All over x minus 2. Now here's where we have to be careful in our substitution step. X is approaching 2 from the left, and so to substitute for f of x, I need to substitute what f of x is for x is less than 2. What is f of x for x is less than 2?
Actually, it's going to 0.
Exactly so. So we're going to plug this guy in. Now, here is the thing that gives students the hardest time, and it shouldn't, but sometimes it does. F of 2 is literally the value that f has when x is 2. What is that value?
1.
It is 1. And so I'm going to substitute for f of 2 the value 2 squared minus 3, because that's what f is. F of 2 is. Well, that was the hard part. The easy part is the evaluation. A quick check of form reveals 0 over 0. So factor it and get limit of x goes to 2 from the left of. Cancel, let x go to 2, and we get 4. And here's what this means. This means that coming from the left here, if I start at x equals 2 and work backwards, I'm going to get a slope of 4. Okay. Meanwhile, f prime from the right at 2 is going to be the limit x goes to 2 from the right of f of x minus f of 2 all over x minus 2. And for f of x here, I must use the piece of f defined for x is greater than 2. And what is that piece?
X minus 1.
It's x minus 1. And for f of 2, I am going to substitute exactly the same value that I substituted for this one, because f of 2 is what you get when you plug 2 into the appropriate domain. And that is 2 squared minus 3, which is 1. Now, it happens to coincidentally be the case that if you were to plug in 2 to this piece, you would get 1 also. And that occurs because this particular function happens to be continuous, right? But they're not all continuous, and that's where the problems can come in. So we need to be careful that when we're plugging in f of 2, we are plugging in the piece that applies when x is 2. Well, this is very straightforward. What does this limit might be? 1. And what this means is that if I come from the right, I start at x equals 2, and I go to the right, then I get a slope in the delta. And so overall, we would say that f prime of 2 does not exist. And this turns out to be the formula for f prime. Good so far? Okay. Now, let's take a look at question number 2. Question number 2 walked you through a somewhat typical kind of thing that can happen when we have piecewise defined functions here. Notice that this function is really similar to 1c, but I just tweaked it a little bit. I made this a different sloped linear function. So let's copy G over to our smartboard. Well, actually, let's start answering questions here, and then I'm going to copy over at some point. So we're supposed to find g prime of x for x is less than 2 and for x is greater than 2 using the derivative rules. This is pretty straightforward. Using our derivative rules, when x is less than 2, what do I get for a derivative? And for x is greater than 2? And right when x equals 2, we're going to have to use the limit definition. But fortunately, they didn't ask me about that yet. So we have a formula for g prime for x's other than 2. Now, find the limit as x goes to 2 of g prime. Here I've got g prime for all x's except x equals 2. That works for me. But it does occur to me that limit from left and right I need to check separately. So I look at the limit as x goes to 2 from the left of g prime. And when I do, then I get, which piece do I use? And as x goes to 2 from the left, I get 4. But as x goes to 2 from the right, I get 4. 4 again. Oh, well, the limit from the left and the limit from the right have the same limit, then the limit overall is that limit. So that I get a very interesting result that the limit as x goes to 2 of g prime of x is equal to 4. And we're happy with that. Questions? No questions. Okay. Now we're going to look at two very similar looking kinds of questions here. Using the limit definition, find g prime from the left at 2 and g prime from the right. We're going to need some space to work here. Okay, you guys help me out. What do I substitute in? The limit as x goes to 2 from the left of
X squared minus 3.
x squared minus 3, and g of 2
Is
is 1. All over x minus 2. Hey, this is the limit we evaluated before. This is 4. And so we found the derivative from the left of 2. Now the derivative from the right. Here comes the big surprise. What is g of x for x is greater than 2?
4x minus 1.
And what is g of 2? It is 1. Why? Because that is the value that we get when x is equal to 2. The number of students tried to plug in 2 here, got 7. But this piece does not apply when x equals 2. What's going on here? Let's do a quick sketch of what's happening. In this particular case, we again have our quadratic polynomial, this part right here. But when we get to x equals 2, our function now has suddenly a jump discontinuity, like so. Just like that. And as a result, when I use g of 2, I have to use 1 in both cases, derivative from the left and the derivative from the right. It does not matter that g of x is 4x minus 1 for x is greater than 2. What matters is that g of 2 itself is 1. Does everybody see that? That's the place where students can sometimes mess up. Well, this has a really interesting implication because when I simplify, exactly so, and when I look at this and I start looking for a common factor and there isn't one, and then I say, oh, wait a second, I forgot to check the form. What's the form of my limit? Not 0, 6 over 0, yeah, which it tells me that my limit is going to be infinite. Ooh. And specifically, as I check the signs here, I see that the top is going to be positive, bottom is going to be positive, and I get positive infinity for this sign derivative. Why? Well, it's actually kind of simple in retrospect. You start at x equals 2, and you go out to the curve right here to get the average rate of change, and then you let x approach 2. What's this line going to do as x approaches 2 from the right? It's going to go vertical. In other words, to have a jump discontinuity, a function must instantaneously jump. It must have an infinite rate of change, a delta y with a delta x of 0, in order to get from here to there to jump instantaneously. So this means then that although my g prime from the left was 4, my g prime from the right was not, and I want you to compare and contrast that with the limits that we had for g prime in our previous work. Notice that the limit as x goes to 2 from the right of g prime is 4, but g prime from the right at 2 was not. Those two are different concepts. Interesting. And a little bit strange. Yes, ma'am.
I put does not exist for the form 6 over 0.
That's okay, but positive infinity is more descriptive. Saying that a limit is infinite is a more specific way of saying the limit does not exist. So, does g prime of 2 exist?
No.
No. Automatically no, because the derivatives from left and right do not agree with each other. Even though the limits from left and right of the derivative do. Questions on that before we take a look at 3? Thank you. Okay, no questions? Fantastic. Let's take a look at 3. If we can. This thing is not coming up. Let's see if this will work. Were you guys able to pull up question 3 on your homework when you did it? Oh, okay. Open my file. And just do a little bit of refreshing. In the 90s, when we all had dial-up, we called it the worldwide wait. We would say, open my file, go get some coffee, come back to the computer. This is struggling to pull up a second. Okay, well, let me, because this is not coming up, what I'm going to do is to just sort of replicate the graph here. Oh, in the other class, there was a quick question. I got 2 of the answers switched on problem number 1C. The 1 and 4 that I got there, I believe in the answers I had them reversed. Yeah, so that was unintentional. Do you have the graph in front of you? Yeah. So what we have here is a graph that looks like so. There. And then it comes around like so. And then it goes up like so. Something like this. And it's a little bit shallower than that and this. Now, because my graph is not exactly your graph, we may have different things here. This is the graph of h of x, and now they ask for derivatives from left to right at -4, 0, or was it 2? 2. And then again over here at 6, which I accidentally drew to 7. So get this guy there. So this is a matter of just reading slopes. To get the derivative from the left at -4, I'm going to place my pencil right here at -4. I'm going to draw myself a little slope right there that goes in the same direction as the curve. And I'm going to ask myself, what is the slope of this line? And it's over 2 up 1, so this is about 1/2. That's it. Same thing happens over here. I'm going to take this guy to get the derivative from right and just draw myself a line, and that line appears to have a slope of about -2, and so that's my derivative. The derivatives are really approximate, really, really approximate. So if you got anything that was a positive number between 0 and 1, that's fine. Here, if you get a negative number that's pretty close to the slope, that's fine. At x equals 2, I think it's pretty clear to see that the curve right here has a nice tangent line that you can put on that curve, and we can get the slope for it. It looks to me like it's over 4 and up 1, something like that. So both of these values are going to be about 1/4. And then at x equals 6, looks like we have a slope of about 1/2 again from the left. And from the right, it looks like we have a slope that's closer to about 3 or 4. We'll call it 3.5. Something like that. So it's just a matter of reading slopes off the graph. Does that make sense to everybody?
I know. So, are they the same like when h goes to 2 and 6 from the right side? 2 to 6 or so?
Yeah, it's going to be pretty similar. Notice I get numbers that are not too far different from each other. Claire?
You just use
Oh, did I? Oh, when I wrote it, yeah. Okay, let me fix that. It doesn't change anything, but in terms of making it parallel structure, yeah.
Do we have to write the negative first?
No. Okay. Good. Any other questions about that? All right. Well, let's actually use this. And what we want to consider today is the question of what happens if f prime of c does not exist. And what we'd like to be able to do is to use some analysis to describe the shape of the curve when f prime of c does not exist. And there are a lot of different ways in which this can happen, but I want to describe four of those for you. And we'll go into some detail with one of them tomorrow. What happens if f prime of c is not exist? The first way in which f prime of c can fail to exist is that if f is discontinuous at x equals c. If f is discontinuous at x equals c. What were our types of discontinuity again? What we talked about? Jump? Point or removable? And vertical asymptote, exactly. And in all three of those cases, because f of x is discontinuous at x equals c, it is impossible to draw a tangent line at that point. And we'll actually prove that fact tomorrow. And a really good example function for this is the function f of x equals int of x. Remember this function? Yep. It has a graph that looks like this. And it has a jump discontinuity at every what? Every integer, exactly so. Well, if you take a look at the graph of int of x, you can see that the slope of that graph is going to be 0 for every point in the interior there. But right when x hits an integer, all of a sudden, boom, there's a jump discontinuity. And to do that, the graph must have an infinite rate of change, but from one direction only, from the left only. So that we have f prime from the left at x is positive infinity when x is an integer. But f prime from the right at x is equal to 0. Isn't that interesting and strange? In other words, if I go to an integer right here, and draw myself a direction that way, I get 0. And if I draw the connected curve there, I have to convert it. We'll go into more detail about the relationship between continuity and differentiability tomorrow. So this is one way in which f can fail to be differentiable. The other three ways are going to all involve functions that are continuous at x equals c, but nevertheless do not have a derivative. And the first way that that can happen can be if f of x has what we call a sharp corner. F of x has a sharp corner at x equals c if the derivative from the left and the derivative from the right have different values. Gotta keep my color coordination. There we go. And the classic example function for this is f of x equals the absolute value of x, which we have seen several times. We take a look at f of x equals the absolute value of x. Then you can see that f is continuous at x equals 0, but when I evaluate derivatives from the left and derivatives from the right at 0, I get different values. What is the derivative from the left? Negative how much? 1. Negative 1, that's right. And from the right, positive 1. The fact that I have two different values here immediately tells me that the function has a sharp corner. Now here's what this means graphically. This means if I take the graph of the absolute value of x and I zoom in to the neighborhood containing 0, I will see that sharp corner no matter how much I zoom in. Even if I set my window size to be negative 10 to the minus 80th to positive 10 to the minus 80th, I will still see those two lines coming in and forming a sharp corner. It will never be smooth at any level of zoom.
What is
So this is the first type of non-differentiability where f is continuous. If we were to summarize, give these words, we would call this first type up here a discontinuity. We would call this type a corner. The other two need a little more space. I'm going to give myself another page. The third type, we're going to say that f of x has a vertical tangent at x equals c. If the derivative at c is positive infinity, or the derivative at c is negative infinity. Now I want to take a minute to consider what this means. And we'll do this by means of an example function. I lost my color coordination again, didn't I? Yep. Let me put it back. This is all. There we go. And for the example function that I want to choose, I want to take a look at f of x equals the cube root of x, or in other words, x to the 1/3. Now, if you graph this function on your calculator, what you will see is that f of x equals x to the 1/3, which is very, very interesting, because it comes in towards 0 like this, and right when it hits x equals 0, the curve goes straight up, like that. And because it goes straight up, therefore, when I draw the tangent to the curve, I have to draw it as a vertical line, a line with infinite slope, essentially. Now, how do I know that it's infinite and not just really steep, right? Because the graph would lie to me. So to demonstrate that it's infinite, I need to actually do the analysis here by computing f prime of 0 and seeing what I get. So, if I compute f prime of 0 using the limit definition, that's the limit as x goes to 0 of f of x minus f of 0 all over x minus 0 this gives me x to the 1/3 over x. Subtract the exponents. 1 over x to the... Yes, exactly. 1 over x to the 2/3 power. Just check the algebra on that and make sure that that's good for you. And it's pretty clear that the form is 1 over 0, so my limit is going to be infinite. And in particular, when I consider from the left and from the right, obviously I'm going to get positive infinity. But from the left, I will also take any number that is negative, close to 0, take its cube root. If you take a cube root of a negative, you get a negative or positive. Negative. And now when you square that number, positive. Aha. So whether I come from the left or the right, I will get positive infinity as my derivative. Here's what this means on the graph. This means that as I am approaching x, 0, from either direction, I'm going to get tangent lines that get more and more positive in their slope. And as a result, my curve goes straight up at that point.
For the f prime receive the positive and infinity and negative. So no matter it goes from the left to the c from the left or right.
Exactly, that's right. It needs to go from left and right, positive infinity, or from left and right, negative infinity. So an example of the second type would be f of x equals negative x to the 1/3. That's a great question. Let me put a note in here for our viewing audience. Slopes get increasingly positive. X close to... Better? Okay. The last type that we're going to consider is a very unusual type, and you will have not seen it before, I don't think. But it essentially combines the idea of a vertical tangent with the idea of a sharp corner. And we will say this: f of x has a cusp at x equals c. A cusp at x equals c if we have two things that have to be true. F prime from the left is negative infinity, but, and F prime from the right is positive infinity. Or vice versa. F prime from the left is positive infinity, but F prime from the right is negative infinity. I did that in the question. Here we go. Now let me show you what this looks like on a graph first, and then I'll give you a fairly simple example of a function that has a cusp. So you guys can cusp. So let's sketch this on a graph. We're going to pick C right here, and we'll make f of c be this value right here. And so what I'm going to do is to come in from the left so that my derivative at c from the left will be negative infinity, but my derivative at c from the right will be positive infinity. And so coming from the left, that means that I need to go vertical with ever decreasing slopes. See that? But now coming in from the right, I need to go vertical with ever increasing slopes, like this. So that my function has a vertical tangent line right here at x equals c, but we have different signs of infinity, so to speak. In other words, we have decreasing slopes from the left and increasing from the right. Does this make sense? Somewhat? Jennifer's not convinced.
Is it like similar with the sharp corner?
It is similar to the sharp corner because we have different things happening left and right. It's also similar to the vertical tangent because we have a vertical tangent line. So it really is in some ways a combination of those two things. Now let me give you an example of what I'm talking about. This is the classic example. This curve, f of x equals x to the 2/3, sometimes I call it the bird curve. Because when you draw the graph of that, in fact, if you have your graphing calculator, you can put that onto the calculator and graph it. Maybe we'll use this window size right here. And I'll put it on my grapher as well. There it went. Please pay attention. Our technology is not paying attention. Okay. Well then, hopefully what you see is this right here. And I call it the bird curve because it looks like those birds that you used to draw when you were in kindergarten. You know? Okay. And so here, it appears to me that we might have a cusp. The problem is, it appears we could also have a sharp corner. It all depends upon whether or not my tangent lines go vertical. So to demonstrate that I have a cusp, I need to actually do the analysis. I'm going to consider the derivative from the left at 0, and I'm going to consider the derivative from the right at 0. And I have to use the limit definition for each of those. So the derivative from the left is going to come out as the limit is x goes to 0 from the left, x to the 2/3 minus 0 to the 2/3 all over x minus 0. Good, that's exactly right. In other words, 1 over the cube root of x. But when I take a number that's less than 0 and take its cube root, I get a negative value, and the form of my limit is 1 over 0. So that means that in the sign analysis, I get a positive value on top, negative value on the bottom, and my derivative from the left is going to negative infinity. These tangent lines here have negative slopes and getting more negative. Meanwhile, the derivative from the right will be the limit as x goes to 0 from the right of exactly the same thing. 1 over x to the 1/3. Again, the form is 1 over 0, but this time the sign on top and bottom are both positive, so that I have positive infinity for my slope there. Just like that. So that I conclude, on the basis of the fact that I have negative infinity from one side, positive infinity from the other, that I have a cusp at x equals 0.
Why not a sharp corner?
Why not a sharp corner? Because to have a sharp corner, I need to have finite positive, or not positive, I need to have finite values that are different from each other. So if I had gotten -1, +1, -2, +2, +3, and +4, any two finite values that are different from each other, that would indicate that I have a corner. So this is like a corner, but it's more specific than that because it involves vertical tangency as well. and it's going to have implications for the graph of my derivative. In the future, when we graph f prime, the graph of f prime will look like this when f of x has a sharp corner. It will have a jump discontinuity. But the graph of f prime will look like this when f of x has a cusp. Does that help?
Yeah.
If f of x, if this is c, and f of x has a corner, then the derivative from the left and from the right will have different values. In other words, f prime will have a jump discontinuity. And as if f of x has a cusp instead, then the graph of f prime will show a vertical asymptote right here. Okay, bell's about to ring. I'm going to do a quick summary of our 4 types of non-differentiability. Bell did ring. Tell you what, we'll do the summary tomorrow, and you can also find it in the notes online that I already posted. See you tomorrow.